Hi everyone, welcome to Math 112. This is Scott. Let's get started. So this class is going to be an exploration of the trigonometric functions. Those are things like sine, cosine, tangent, which you may have seen here and there perhaps in your scattered wanderings throughout the mathematical world. But in this class we're going to cover them very specifically from the pre-calculus perspective. And when we're doing the trigonometric functions in the whole mindset of calculus, which also includes all of the mindset of physics and everything like that, then we adopt a slightly different view of angles from what we would typically do in a first trigonometry class. So what we're going to do in this first section is get the lay of the land as far as what angles are to us and how we measure them. Angles and their measurements. All right. So first off, here's the basic picture. So the basic idea is that for an angle, rather than just thinking of it as being like a wedge or like a V shape, we're actually really going to think of an angle more as a direction of maybe even rotation. So an angle represents, say, an orientation. Relative to the origin. Alright, so it's a vague way of putting it. Let's make it a little bit more concrete. And so what we are going to do first is discuss standard position. So standard position. So we are talking about the XY plane and, just classic Cartesian plane as first formulated by René Descartes, the person who invented what is now called analytic geometry, which was the first time in history that algebra, which is an old science, and geometry, which is an even older science, were fused together into one subject. So we're going to be using the classic XY plane, and what we're going to do is start at the 3 o'clock position, so that's the eastern side here, the x-axis, the positive x-axis, and move in a counterclockwise direction by a specified angle. So standard position is this. So imagine the unit circle. So what that means is circle radius 1, which means that's 1, that's 1, that's negative 1, and that's negative 1 as well. So unit circle. So the circle of radius 1. So that's what that means. And then what standard position will describe is a specific way of locating an address on the xy plane that is on the unit circle by means of an angle. So represent an angle in standard position by taking a unit circle centered at the origin and start at the point 1, 0. So start at 1, 0 on the unit circle centered at the origin. And then just move counterclockwise by a specified angle. So start there and move counterclockwise. The specified angle. Now, what this means is there is a specific direction. It's sometimes called the trigonometric direction. Actually, I think in French, even the phrase counterclockwise, what is frequently called, they actually say sens trigonométrique. But we move counterclockwise the specified angle. And when we have a specified direction like that, counterclockwise in this case, that means that we can use negative values to represent going the other direction. So if the angle is negative, go clockwise. All right, so what that means is then, under this framework, we can use any kind of number to represent an angle. It can be a positive number, it can be a negative number. If we're talking about degrees, it can be anywhere from negative infinity to positive infinity. It could be bigger than 360 degrees, and it could be more negative than negative 360 degrees. And the only difference that makes is the direction. And this is the standard meaning that negative has in math. It means that there is some direction that is the regular one, and we're going the other way. So for example, negative coordinates mean that our standard direction being right, we actually go to the left if we're talking about the x-coordinate. Or for y, the standard direction is up, so negative means go down. And just in general, negative the kinds of values that can be negative are any kinds of values that are inherently directed one way or another. Same way, temperature, we can have degrees above 0, and then we can also have degrees below 0. And so it makes sense for temperatures in Celsius or Fahrenheit to be negative. Not as much Kelvin, but that's neither here nor there. All right, so now let's see some examples. Okay, and also, so here would be an example. Let's say we were talking about an angle like that. And the standard letter we're going to use for angles is the Greek letter theta. So actually, let's even put that in there. So notation. Notation. We use Greek letters like that one, which is theta. Sometimes we use phi, so it's kind of like that. Maybe we'll use alpha, beta. Etc. to represent angles. So this is the way we will by default represent our angles, especially when we are using a sort of unit circle framework. When we talk about triangles in particular, then we might be inclined also to give them names like A, B, and C, uppercase if it's the angle we're talking about, lowercase if it's the side, in a sort of standard triangle notation. But these are the Greek letters that we will use, and let's Let's now take some examples of angles in standard position. Alright, so the easiest way to do this will be to just list a few angles, draw ourselves a big circle, and then label the corresponding points wherever we find them. Alright, example. Draw. The following angles. In standard position. Alright, so let's just take this for a test drive here. So first, let's just go with some relatively easy to think about angles. 135 degrees. So I just have to find that on the circle. How about something like 270 degrees? Alright. Now, we can get bigger than 360 if we want. We could go, for example, 390 degrees. Let's see. We can have negative numbers. We can have negative 120 degrees. We can have positive numbers that are, we can have 0. How about that? 0 degrees. By the way, anytime your angle is measured in degrees, make sure that you actually write the little degree symbol. That is not optional. Alright, and then the last one, let's just say negative 680 degrees, something like that. Oh wait, one more thing here. How about this? How about 240 degrees? Alright. So these are all possible angles that we can represent in standard position with no fuss, no muss. If we were talking about angles in the sense of being parts of triangles, a lot of these wouldn't make that much sense. Try to draw a triangle that has a 270 degree angle in it. It isn't very sensible. But what it does make sense as perhaps a rotation. If you have a dial, it makes perfect sense. Rotate the dial 270 degrees. Okay, so let's just have ourselves a little circle here. It's not a great circle, I'll be the first to admit, but oh well. It's the circle we've got. Okay, so let's start off before we label any of these specific ones. Let's just put in some of the key landmarks here. So here at the 3 o'clock position, that's where we would find 0 degrees. A 90 degree angle, so remember we are working our way counterclockwise, a 90 degree angle would be found up here. Over here would be 180 degrees, and then down here would be the 270 degrees. Alright, so it's just adding 90 each time around, and if we wanted any of the halfway marks on each of these quadrants, those would be the 45, or here it'd be 90 plus 45, 180 plus 45, etc. Alright, let's identify where some of these angles would be. So 135 degrees. So if we think about that, the easiest way to visualize that is 90 plus 45. Okay, well that makes sense. So we are starting at 0, we're going 90 degrees, we're going 45 more degrees. So that's where we'll find A. As for B, that one's already there. And technically these are angles, so they would frequently be written as rays coming out of the origin. Okay, so that one's there. 390 degrees, how should we understand that? Well, if we think about it, it's 360 plus an extra 30. So that means we have gone full circle, so we've rotated the dial all the way around, and then it's gone 30 degrees more. So that'd be a third of the way up here, so like maybe right there. Okay, now, how do we make sense of a negative angle here? The negative value of the angle represents not going in the standard direction, counterclockwise, from the x-axis towards the y-axis. Instead, it would represent going backwards. So we go 120 degrees in the opposite direction. So this would be going down here. So this would also be the same thing as negative 90 degrees. So it's negative 90 plus an extra 30, so we can figure out that'd be right here. Or there are other ways of thinking about it too. Maybe you prefer to think of it as being a third of the circle this way, although thirds are a little bit harder to represent accurately. All right, which one is this? Was D? All right, let me just label these. All right. As for E, that one's this one. It's already there. And while we're at it, we can also note that this is the same spot as where we would end up at 360 degrees. But again, let's stick to the brief here. All right, so those ones are easy. This one is a little bit less easy. Let's think about it. So 680. One thing you could do is you can figure out where it is by just putting it in terms of 360s to start with. So cut it down to size. So it's negative 360 degrees, and then what does that leave us? That's plus another negative 320. Which we'll figure out a better way perhaps of conceptualizing that, but essentially what we do is go all the way around in the wrong direction and then almost the whole way around again. And how far short do we fall? So we're 320, so that's 40 degrees shy of a second rotation. So we've gone all the way around, almost all the way around again. We're just 40 degrees before the second full rotation. So we'll just call it there. So just put it in terms that are close to more familiar angles. All right, and then for 240 degrees, where is that one going to end up? Well, if we go all the way around, not all the way around, if we go all the way to the other side, that's 180, and then we would be looking at 180 plus 60 more. So it's 180 plus 60 more, which is the same as going 270 and back and 30 less. So actually D and G end up at the same spot. And what that means is, and we've seen this already here and here, what that means is sometimes you can arrive at the same point from different angles. Maybe one is positive and the other is negative. Maybe one is all the way around the circle and the other is still within the first rotation, something like that. And the term for these types of angles are coterminal. So note, angles that end at the same place in standard notation, or standard position, I should say. Are called coterminal. Coterminal angles. So that's ending together. All right. So this is degrees. We'll talk a little bit more about some of the details of degree measurements, but it's the system of measuring angles that I think is most familiar to most of you. So everybody knows what a 90-degree angle is. If somebody says it's like a 45-degree slope, we all know what that means too. we have ideas. We know what it means to turn a 180 or a 360, which would be all the way around. Things like that. So we already are pretty familiar with degrees. But there's another system for measuring angles called radians. And this will be actually our default measure going forward after we've learned what it is. All right, so here's how radian measures of angles works. So radian measure. So the way a radian works is, imagine that you are in the business of drawing out the angle in standard position. What your radian measure represents is how many radius lengths you travel as you go from the 3 o'clock position to your angle. So radian measure. So this indicates how many radius lengths are traveled when going through the process of locating the point. In standard position. So what this represents then, in other words, is how far an ant would have to travel going from the point over here, which if we're talking about the unit circle is always going to be 1, 0. It's going to be how far the ant would travel in going from point A here to point B. So let's say the radius was 1. Then how far it is here, this arc length, represents the radian measure of the angle. Sorry. So that's a very abstract way of putting it, and it's really pretty hard to sink your teeth into this kind of a description. So the easiest way for us is going to be to just figure out the radian measures of different commonly found angles. So radian measures of common angles. All right. So let's start with 0 degrees. So 0 degrees. So if you're at 0 degrees, that puts you just right on the east coast of the unit circle. You have not moved at all, and so that's 0 radians. So you have gone 0 times the length of the radius. Now, let's say you go all the way around the circle. How many radius lengths have you gone around in order to do that? Well, if you march all the way around the circle, then we actually already have a way of measuring that. That's called the circumference of a circle. And the circumference of a circle is 2 pi times the radius. And that means precisely 2 pi radians. Okay, now from this we can scale up and scale down to all of the angles that we are going to know and love throughout this whole course. So for example, if 360 degrees is 2 pi, then 180 degrees would just be half of that. And I don't have to actually write radians each time. It turns out actually that radians are a measure that is called a dimensionless quantity. And it's not actually a unit. It is actually a ratio. It's the ratio of how far you've gone to the radius. And so any units that it had, whether they were centimeters or meters or miles or whatever, those would actually cancel each other out. So it's actually just a pure number. It doesn't actually have units. So we won't actually usually write radians after a radian measure. However, the degree mark after a degree measure is totally obligatory. You cannot omit that at any point. If your measurement is in degrees, you must write the degree mark. Okay, well let's do just what we did again here and cut it in half. So if 180 degrees is the same as pi radians, then 90 degrees would be the same as pi over 2. And while we're at it, we might as well cut that in half again. So then that means 45 degrees is pi over 4. And then let's see what else. So how about 30 and 60? Well, the easiest way to think about the 30 is take the 90 degree one and cut it into thirds. So in other words, multiply it by a third. So 30 degrees is pi over, so then it would be multiplied by 1 over 3. So it would be pi over 6. A sixth is a third of a half. Okay, well, what if we want 60? Well, that would be just doubling this one, so we can just do that. So 60 degrees is equal to pi over 3. Let's see, other big ones. How about 120? While we're here, just double that again. So that'd be 2 pi over 3. And what else we got here? How about 270? That's one we will make lots of use of. What is 270? So if you think about it, that's 90 times 3, so it'd be 3 pi over 2. And now that we've figured out a few of these, it gets a little bit boring and tedious to go around coming up with every single possible combination. So what we should do maybe instead is just make ourselves a nice little circle and label these key landmarks all along the way. Alright, so right over here we have 0, which is also the same point as 2 pi. They are coterminal angles. And then, let's see, working our way around. It'd be easiest if we just go here for the 90 degree angle, which is pi over 2. And then over here, let's say that one is the pi over 6. Sorry, pi over 3, I mean. 60 degrees. Yeah. Classic mistake. Pi over 4 is there. pi over 6 would be over here somewhere. These are not really to scale exactly, they're just put in rough correspondence to the order that we would encounter them going around the circle. And then let's just see here. Let's just put these in like so. All right, now let's help ourselves with some more. So the 120 degree mark. So that one was the 2 pi over 3. Right over here, that would be 135 degrees, which is let's see, the best way of thinking about that, 90 plus 45, so that's a half plus a quarter, it's 3/4. Let's see, other important places. How about over here? Let's go a little bit closer up like that. Yeah. I don't know. So when you do this just freehand without a protractor or anything, your diagrams become more of a cartoon than a photograph. So you just have to accept that. There are plenty of unit circles to be found on the internet that can draw these things a lot more precisely than is worth our while to do. So I apologize for nothing. All right, now over here, where are we? So if you think about this angle, it's 100. So it's 180 minus 30 degrees. That would be the next of the sort of superstar angles that we'll be looking at. So 180 minus 30 degrees. That means it's 150 degrees. And then if we think about this over here, try to find a convenient thing. 150. Well, that's the same as what we just said. 180 minus 30, so it's pi minus pi over 6. So if you take 1/6 away, that leaves you 5/6. So 5 pi over 6. Over here we have pi. Over here, let's just start with the halfway mark, just easier to draw. Okay, so down here we went from pi and we added an extra pi over 4, which is 45 degrees. So that means that we've got 5 pi over 4. All right, let's see, how about over here? So for this would be 180 degrees plus an extra 30 degrees. And so that'll be, and so then that one would be pi plus pi over 6 is 7 pi over 6. Down here, this would be 270 minus pi over 6 would be one way of thinking about it. Alternatively, it's 180 plus pi over 3. Different ways you can try to think of it. Either way, you get to the number 240 degrees, which we already saw. And if we think about it, 240 degrees, that's 2 times 120. So this means this would be 4 pi over 3. Down here, what we have, and we're just doing this once, so we never have to do it again. 3 pi over 2. Over here, we're getting to the tail end here. So if we think about it as a negative angle, this is negative 45 degrees, or if we think about it as a positive angle, it's 2 pi minus 45 degrees. And so what that means is that it's 2 pi minus pi over 4, which would leave us 7 pi over 4. So 2 pi is 8 pi over 4, minus 1 pi over 4, leaves us with 7 pi over 4. Okay. All right, what else we got here? How about this one down there? So what's the best way to think about that angle? So first off, once you get past the South Pole here, I always think it's easier to relate it to the 0 or the 2 pi than it is to try to add weird fractions like 3 pi over 2 and like nobody, I don't think anybody looks forward to doing things like 3 pi over 2 plus pi over 6, because That's two fractions with different denominators. Nobody's idea of a good time. Okay, so let's think about it instead as 2 pi minus 60 degrees, so minus pi over 3. So 2 pi is 6 pi over 3. Take away one of those pi over 3's, you're down to 5 pi over 3. Alright, and now the last of the 16 key points, as we will call them sometimes, around the unit circle. These are the points that we will know and love by the end of this term. Well, at least you'll know them. I can't guarantee that you'll love them, but I do. So here, the position of this point is 30 degrees short of the full rotation. So that's 2 pi minus pi over 6. So that's 8 pi over, sorry, so that's 12 pi over 6 minus 1 of the pi over 6 makes 11 pi over 6. All right, so that's where the various important locations of angles are in the radian measure. Okay, so that is all a fun little exercise in trying to figure out what things are as they go around the circle. But let's actually come up with something a little bit more scientific for doing conversions, because it's all well and good to work from known angles down to other ones by putting them together in various clever ways. But sometimes you just need a formula. Like, what if I had said 23 degrees and I wanted the radian measure of that? Who knows? So let's figure it out. So let's just think about how to convert between degrees and radians. Converting between degrees and radians. All right. So, like so many other kinds of unit conversion, what this is going to rely on is what's called a unit fraction. When you look over this table of values that equal each other, look for one that would be very convenient for using to convert from degrees to radians. And the one that strikes me as the most convenient is this one right here. 180 degrees equals pi. So if 180 degrees equals pi, then that's what we will use. So the same way you can convert between miles and kilometers, if you know either what 1 mile is in kilometers or 1 kilometer is in miles, if you know either one of those facts, then you can make a fraction that will enable you to convert between them. So let's see. Let's say first degrees to radians. All right. So you take the degree measure, and we just multiply it by. Now we just need a fraction. The top is either pi or 180 degrees, and the bottom is the other. And the key is we need degrees to cancel and radians to survive. This is the same way you would do any other kind of unit conversion. Like, let's say I wanted to convert, I don't know, miles to kilometers is a good one. Then if you are starting with miles, you want miles to cancel, kilometers to be left. The same thing here. So then what that means is we want the radians to be up here, 180 degrees down here. And now let's say we wanted to go the other way, radians to degrees. So then the way that would work is you do whatever the radian measure is, and you would just multiply it by the inverse of this unit fraction. So you would do 180 degrees upstairs, pi downstairs. And then you would just simplify. So for example, let's say degrees to radians first. What did I say before? 23 degrees. How about that? It's a nice random angle. Okay, how does that work? So 23 degrees. All right, so 23 degrees times. So effectively here what we're doing is we're multiplying it by 1. Pi and 180 degrees are the same thing, and so this over itself equals just 1. Now, if we want this to be a fraction that involves pi, we are free to have it be such. It's not a very appealing one. It's 23, like the degrees basically would be the only thing that would cancel. 23 pi over 180, which, if that could reduce, that would be a beautiful thing, but it can't. I mean, look at it. 23 is a prime number, so there's not much, so it's pretty slim pickings when it comes to any common factors that could be canceled from the two of them. But if you wanted an approximate number, you could just pull out any kind of calculator and have it figured out. By the way, don't use 3.14 for pi. Use whatever the calculator's native pi button is. It'd be the easiest thing, because otherwise you're rounding, and a rounding is a slight lie, and you want to avoid lying whenever you can. Math is the one field of life where lying does not, you cannot ever get away with it. So here we go. So apparently that is about 0.401. We'll just round to a few decimal places. All right. So what this means is, if you trace out an angle of 23 degrees, then you will have gone 0.4 of a radius. So you'll have gone 4/10 of a radius in walking 23 degrees around a circle. Okay. How about something like, and then, if you can do one of these, you can do a million of them, but let's just see one where it cancels a little better. How about, where there's a little bit more reducing of the fractions? How about 12 degrees? 12 degrees times pi over 180 degrees. Again, the degrees basically are the only thing that cancel. Degrees you do write as though they are units. Radians, though, you would typically leave omitted. So here, if we look at that, what's that going to be? 12 pi over 180, and we can already see that that is definitely going to reduce. The question is how much. So certainly they share a common factor of at least we can tell 6. Maybe it gets better than that. So for example, if I divide it by 6, then that'll be 2, and this will be 30. But wait, there's more. Cancels even better. And we've got 1 and 15. So we've got here is pi upstairs, 15 downstairs. So 12 degrees would be pi over 15. And you could do this even for angles that we already looked at, like, I don't know, or ones that we were already dancing around, like let's say 135 degrees. Oh, and if you did want the decimal here, just because it might be the case that you did, depending on the context, maybe you'd actually want to know what the arc length of this little journey was, then you would go. So if you travel 12 degrees along the circle, you're going to have gone approximately, turns out, 0.21 or 0.209 radius lengths. Okay, and last one, let's just say 135. If you can do any of these, you can do a million of them. So let's say 135 degrees times pi on top, 180 on the bottom. Just remember, you want the degrees to cancel. That's the whole point. You want, when the dust settles, there to be no degrees left in your fraction here. Everything should just be in terms of pi, and they'll just be in radians. There should be no degrees left. All right, 135 upstairs, 180 downstairs, and I'll put the pi there. It's kind of the usual place of putting the pi. All right, so then where do we have any cancellation? You might be faster at this than, or you might be slower, but the one thing I can see for sure is these are both definitely divisible by 5. So if I divide them both by 5, so the easiest way to divide by 5 is to just double it and then take away a decimal place. So that'd be 27, and then this one divided by 5. If you just double it, and take away a decimal place, 36. All right, and now wait, 27 and 36. Those cancel even a little bit more. And what do we have? 3 and 4. So in other words, 3 pi over 4. Which, sure enough, is what we had settled on when we were drawing out that unit circle. And if we are just curious, because we might be, 3 pi divided by 4. Just calculate away, and so it turns out if you wander 135 degrees around a circle, you will have walked 2.356 radius lengths along the way. So alternatively, if you rotate something that far, that's how far a point would be moved. Like if you rotate a bicycle tire by 135 degrees, a point of it will go 2.356 times the radius on its journey. Okay, so that's degrees to radians, and to do radians to degrees, very similar. Very similar indeed. All right, radians to degrees. So let's say, so let's do an example. Let's say that we wanted let's start with one we already saw before. How about from the unit circle? How about 7 pi over 6? Okay, so what do? So we are starting in radians and we want to end up in degrees. So that means we are not canceling the degrees. The degrees must survive. So 180 degrees goes on top and the radians go on the bottom. So the pi goes on the bottom. Okay. So what's that mean? That means that we're going to cancel the pi's, and this will frequently happen. Sorry, I did not format this the same way as I was doing the previous one. So let's just reformat it. So 7 pi over 6, and then so you write what the thing is, and then you start working on it. Okay, so 7 pi over 6. So the way you do that, again, is you multiply by whatever version of the unit fraction works in this case. So it's either 180 over pi if you are going from radians to degrees, or it's pi over 180 if you're going from degrees to radians. Okay, so here we are again, and the pi's do cancel. It's not a mistake, it was just not formatted the way I wanted. Alright, and then we can look for any other common factors that are shared by the top and the bottom, and sure enough, I can see that 6 and 180, they not only share a factor, but actually the 6 goes into 180 degrees, namely 30 times. So what do we got here? So clear away all the rubble, the pi's are gone, the 6 is gone, we're down to 30 up there. So if we put it all together, we've got 7 times 30, which is 210 degrees. So the degrees survived. You would treat those the same way you would treat miles, the same way you would treat kilometers. They behave like a unit, whereas radians don't. Okay. Okay, so how about now something like um, negative 2 pi over I don't know 5. So something a little bit off the beaten path of the unit circle that we were exploring before. So those angles that we saw when we were drawing out the unit circle, those will be the ones that we'll encounter most frequently. But other angles obviously exist, so we just have to accept that and deal with it the same way. Negative 2 pi over 5 times. Alright, so what we have once again is a case where the pi's are what we want to cancel and the degrees are what we want to survive. So we just put the 180 degrees up there and the pi on the bottom. Alright, so now we can just roll up our sleeves, get to work. What cancels? Pi's cancel each other. The 5 goes into the 180, and once again, to divide by 5, double the number and take away a decimal point. So it would be 360, and take away that 0 at the end. Alright, and that's everything, it looks like. So what have we got left? Well, it's still going to be degrees, and it's still going to be negative. A negative degree measure will correspond to a negative radian measure. That shouldn't surprise us. And then 2 times 36 is 72. So negative 72 degrees. Now, just for the sake of it, what about just 1 radian? 1 radian. Just so we know roughly what we're talking about here, how big is a radian? Like just 1 radian. So let's think about this. First off, just without using that formula, let's just think in terms of the definition. So okay, so we're starting right here. We are supposed to march 1 radius length around the circle. So we have to go that far up around the circle. So if we sketch that out, so this would be 1, 1, and then that would be approximately 1 radian. So looking at it, it looks like, you know, somewhere around 60 degrees, which shouldn't surprise us. To go for this length to be the same as that length means that this is just like a curved version of what's basically an equilateral triangle. However, it's not quite exact, obviously, because equilateral triangles have straight sides. This one has a curving side, so it's not going to be actually exactly 60 degrees, but it is in the ballpark. And let's just see. So 1 times 180 over pi. So if 180 degrees equals 1 pi, then we would just divide pi, or 180 divided by pi. Let's just see what that gets us. 57.29, and here I'm just going to go ahead and round that to 57.3 because that's I think the sort of standard historical figure that was used by like engineers and such whenever they were doing the conversions. So 57.3 degrees. So that's approximately what 1 radian is. Now, it just so happens, by the way, that this is, for me, a relatively easy number to remember because I also teach Math 111 pretty frequently, and 5730 is pretty close to the half-life of carbon-14, which comes up in some logarithm examples. So 57.3, a number, good to know. So 1 radian, turns out, is approximately that. Now, if you wanted to do 2 radians, 3 radians, half a radian, what have you, you can just put those numbers in where there used to be a 1. So not too hard. All right. Well, that's converting between the old system that we're pretty used to and the new system that we just learned. But speaking of that old system that we thought we were so used to, there are more elements to the degree system than we've usually usually than we will usually consider in these contexts, but they do come up from time to time. So degree, minute, second format. So DMS, or degree minute second format. This is an alternative way that angles are sometimes mentioned when it's in degrees, and it is instead of giving it in terms of a decimal, like 31.7 degrees or whatever, it would be representing it in terms of minutes and seconds. So degrees, so degree, minute, second format is another way to write degree measures of angles. And the way we write it is just, for example, let's say 31 degrees, and then, I don't know, 27 minutes. And the way you do that is with one tick mark. And then, let's say, I don't know, 15 seconds. So 31 degrees, 27 minutes, 15 seconds is how you would read this. So these are seconds, or sorry, minutes. And these are seconds. Where you will see this most frequently in modern contexts is things like longitude and latitude. It used to be much more common than it is now to write degrees in this rather than as a decimal. However, that has gone way out of fashion, and now longitude and latitude, like a GPS coordinate type thing, is the main context when you would still see this old format. Other places would be in navigation, so it is frequent, so I guess again because it's longitude and latitude, but also star. So the orientation of the sky when you're giving the position for a telescope. You might also see these sorts of things in an old-timey observatory. But the meaning of it is 1 minute. 1 minute is a 60th of a degree, just like a minute is a 60th of an hour, and 1 second is a 60th of a minute. So these are based on the same conversion. 60 minutes. Minutes equals 1 degree. And 60 seconds equals 1 minute. So just like with timekeeping, so this is the same basic system as for timekeeping. If you're curious, in extra precise measurements, if you wanted to go down to the next level, so rather than seconds, it would be like thirds. So you'd say like tertiary. So literally the meaning of this is there's degree first, or hours if we're talking about time, and then there's a minute part of a degree. That's why it's called a minute. And then there's like the second degree, like the second level of minute part. And the reason why 60 is used, you may have wondered this whenever you first learned how to tell time, instead of something like 100, is that 60 was the way fractions were written in ancient Greece. They didn't use a decimal like we do. they broke their fractions into 60ths. And the reason for that, the reason why 60 is a convenient number for fractions to be broken into, is that 60 is what's called highly composite. So one of the great flaws in a decimal system such as ours is that a lot of common fractions require infinite repeating decimals. Like even, very, very common fractions like 1/3. 1/3 is a very common fraction and it can't be expressed except with an infinite repeating decimal. And the reason for that is because the number 10, which is the base of our number system, doesn't have very many prime factors in it. It only has 2 and 5. So that means only fractions whose denominators are combinations of powers of 2 and powers of 5, those are the only fractions that will not have an infinite decimal. Other than that, all other fractions will have an infinite repeating decimal. Now, 60 is a more convenient base for avoiding that issue because a lot more things go into 60 than go into 10. So, for example, so if you're 60, like your factors are 1, 2, 3, 4. So you can get thirds, by the way. That's interesting. 5, 6. So the first fraction that would have an infinite repeating decimal part, or here it'd be hexadecimal, something like that. Part would be sevenths. So this is an old-timey system. It's based on the Greek and before that the Babylonian way of representing fractional parts of numbers, but it lives on in particular in longitude and latitude, so we might as well cover it. Now we can convert between this, which is called the DMS format, and what we'll just call decimals in degrees, based on this understanding. So we can also write it like this to be a little bit more suggestive: DMS with the little degree symbol, and then one tick mark for minutes and 2 tick marks for seconds. And decimals. In degrees. Okay, so let's figure out how this would work. So converting between DMS and decimals. So let's go DMS to decimal first. All right, so DMS to decimal. So this is not so hard to figure out. You just think, okay, it'd be degree plus, and then basically you just take the minute part, and that would be 60ths. So minute over 60, and then for the second part, oops, I almost wrote 15 based on our example. For the seconds, you would just do seconds divided by, and you might think 60 again, but then you realize, oh no, we already had a 60th. It's a 60th of a 60th, so that'd be 1 over 60 squared, which is 3600. So just be that plus that plus that. So for example, this is very, very, very straightforward. You just translate each thing basically into what it literally means, and you just let technology calculate for you. So for example, 31 degrees, 27 minutes, 15 seconds. That would equal 31 plus 27 60ths plus 15 3600ths. By the way, writing that as 360 is one of the most common errors you could make here. I'll just put a degree around the whole thing, because really it's the overall result that has the degree symbol. I guess, yeah. Awkward. It's an awkward thing to write. All right, but let's see here. So 31 plus 27 over 60 plus 15 over 3600, and you may think, oh, do I have to do any kind of reducing the fractions along the way? No, remember our whole goal here is to turn it into decimals. So sooner or later, we're reaching for a calculator, and we'll just see what we get here. So I just entered it precisely as I wrote it there. And what is that? 31. Yep, makes sense. 31 equals 31. And then the other part, the part that is the minutes and seconds, comes to 0.454. So I'll just round it to 3 decimal places. Problems that involve this in your homework, for example, will always specify how much they expect you to round it. So they'll say how many decimal places, and so you don't ever have to be in doubt about that. Okay, so degrees, minutes, seconds into degrees and decimals is very quick and easy to understand. The biggest place where you might make a mistake is right there, the third term. Most common error there would be to write it as 360. Now, the more interesting thing is the other direction, which is decimals to degrees. Sorry, decimals to DMS. So decimals to DMS. So the way this works is, if I have the angle, the degree part is just the integer part of the decimal, and then you take what's left over and you multiply it by 60. So to get minutes, take the decimal part and multiply by 60. So it's 60 minutes to a degree. So if you take a fraction of a degree, multiplying it by 60 will tell you how many minutes it is. Okay, so then the integer part would be the minutes, and the fractional part, the part with the decimal, can be multiplied again by 60. To get the seconds. So again, it's hard to sometimes understand a description of a process when in fact the actual process itself is much easier to get your mind around. So let's just make up an angle here. Let's say 15.721 degrees. 15.721 degrees. So that looks like the kind of degree you might come up with while you were out in the surveying field calculating away. Oh, but the equipment you're using requires it to be calibrated in terms of the minutes and seconds. Okay, well, let's just see how that works. So first off, the degrees is the degrees. So the integer part here, 15 degrees is 15 degrees. There's no question there. The only thing that changes, the only way that it's expressed differently is on the fractional part of the degree. Okay. So that part is good. 15 degrees is 15 degrees. Nice and simple. Okay. Now we have to untangle this part. So 0.721 times 60. So we scale it up by 60, and that'll tell us how many minutes there are. Okay, well, I'm gonna try that. 0.721 times 60 So I just entered it as I had pronounced it, and it's 43.26. Okay, well, that part is the minutes. So 15 degrees, 43 minutes. Now how many seconds? That's where the 0.26 comes in. So now, just multiply by 60 again. So we're basically, it's like we're amplifying the fractional part by a factor of 60 in order to see it better. So, so we amplified the fractional part of degrees to get the minutes, and now we're amplifying the fractional part of the minutes to get the seconds. So 0.26 times 60 equals 15.6. All right, now here, when it comes to rounding, the instructions in your textbook will typically be to round it to the nearest second. So that means after this point, you would just do standard rounding. You would just round up if it's above 0.5, down if it's below, or 0.5 or below. So then that would be about 16. Okay, so we round it and we get 16 seconds. So 15 degrees, 43 minutes, 16 seconds. And for what it's worth, this is actually the exact same process you would use if you were doing a calculation and it was involving time with and you had a decimal in hours and you wanted to change it to hours, minutes, seconds. Like let's say you had some calculation and you discovered that that the high tide was going to happen 2.618 hours after noon. Well, then what you could do is you could use this to figure out the minutes and the seconds that would go with that. And a very similar process, by the way, also can be used for things like feet. So if you wanted to go from a decimal in feet, like you had 3.81 feet, and you wanted to change it to feet in inches, you do a very similar thing. You just multiply by 12. Whatever the increments are, this is the standard process for converting it into from a decimal to some other increment. Actually, this is also the process that you would use if you were trying to convert a number from one number system to another. Like if you wanted to convert a number from decimal to binary, you would do a very similar thing. You would double the number. You would double the fractional part, and then so you just multiply it by 2 instead of by 60. So it's, or if you wanted to use a base 20 number system, similar thing here. So this is a general procedure that can be used in a lot of different contexts. Alright, the next thing that we're going to talk about is just one more note about coterminal angles, then after that one last topic, and then we're done. So coterminal angles. So I just wanted to follow up on something before and just mention something about when two angles are coterminal in degrees and radians. So once again, these are angles that have the same position in the same point in standard position. So they're two angles that end up in the same place, like 90 degrees and maybe 90 plus 360, so 450 degrees. So what makes an angle coterminal is that you have gone around some number of rotations. So what that means is two angles are coterminal whenever the difference between them is a multiple of a full circle. So 360 degrees or 2 pi radians. So if you ever want to know whether a pair of angles are coterminal or not without the trouble of plotting them in standard position, you can just calculate their difference. So just subtract them, and if the difference is a multiple of either 360 or 2 pi, and it can be a negative multiple as well, then sure enough, they are coterminal. All right. Now the last topic of the section here has to do with arc length and sector area. All right, so let's just think about this for a second here. Arc length, sector area. So what we're talking about here is a section of a circle, and we are no longer necessarily just talking about a unit circle here. We could be having a circle of any arbitrary radius. So we'll just say r, and an angle theta. Then, by the way, the arc length here, we use the letter S. So the letter S is used because it comes from like spatio, it's like the space that it travels. By the way, R for radius. The word radius literally means like a root. It's the same basic word as you get with radical or radish. Radial, and as for theta, it's just a generic letter for an angle. Okay, so arc length and sector area. So there are two equations that we have here, and they're both actually kind of they're either straightforward in themselves or they're based on something straightforward. So first off, arc length. Arc length. So S equals. Now the way this works is you basically just use literally the definition of what a radian is. So radian is how many multiples of the radius you have traveled on your journey. So the S here is going to be equal to theta times r, where theta is specifically in radians. Now, if theta is not in radians, then that requires you to actually have to do some work. But oh well, sometimes it happens. So when theta is given in degrees, easiest thing would be just convert it. Convert it to radians first. Okay, so this is an equation, and it's actually just a straightforward application of what the definition of a radian even is. Now, for the area, it's actually not quite as straightforward, but it is but it's based on something straightforward. So the area is equal to, and first I'll just give you the formula, and then we'll see why I say it's based on something relatively straightforward, at least a straightforward line of reasoning from a well-known fact. So it's 1/2 theta times r squared. Now you may say, I don't know what he's talking about. There's no way that's based on anything familiar that I've ever seen. But it actually is. It is a version of the classic formula that the area of a circle is pi r squared. So you can see an r squared here, and you can imagine that maybe they have some relation. And the relation is that essentially it takes theta as being some fraction of the circle. And in particular, theta over 2 pi equals the fraction of the circle that this happens to represent. So, excuse me. So theta over 2 pi is the fraction of the circle that theta happens to have encompassed, and that means then that the area of the sector would be theta over 2 pi times pi r squared. And then the pi's would cancel, and you'd have just 1/2 theta r squared. So that's the line of reasoning that leads to this formula. Seems like a strange formula, but in fact, actually, it's not as strange as it seems. It's just saying that your angle here is a piece of a circle, and based on what fraction of the circle it is, that's the fraction of the typical area that it would have. Now we can actually use either of these equations to solve for any of the three missing pieces. So let's just do some examples. Find the missing value where, in the first edition, arc length let's just say we have something straightforward. We have theta equals pi over 6, radius equals, I don't know, 2 meters. So here, by the way, we should start having some units on our radius, because now we're talking about an actual length. So, okay, let's say that. All right, well then, S is equal to pi over 6 times 2 meters is equal to pi over 3 meters. Those would cancel a little bit. Now if we're going to be talking about meters and such, then we probably want to have this as some sort of a decimal approximation so that we can actually understand it. So it's 1.047 if I go around to 3 decimal places, which I will, meters. Okay, so that was a missing arc length. Let's see, how about if we have, so what if we have the angle not in radians but in degrees? Theta is equal to 70 degrees. Radius is equal to, I don't know, 8 feet. S is equal to, who knows? That's for us to find out. Alright, so let's see here. Well, S is equal to theta times R. Yeah. Well, theta, if it were in radians, could just be plugged right in there, but it can't be. So theta equals 70 degrees times, now the quick fraction here is 180 on the bottom, pi on the top. And I can see that those are going to cancel a little bit, and going to give us just 7 pi over 18 radians. So they both have a factor of 10, is the cancellation that I did, which means then S is equal to 7 pi over 18 times 8 feet. And that's going to equal, so I mean, I can see like I mean, if I wanted to do some, if I wanted to calculate it, like reduce it beforehand, I could, but there's not really any point in doing that. So let's just plug it in and find the answer. So 7 pi over 18, was it? Times 8. 9.774 feet. Now here's an example of what I was talking about. If you wanted that into degrees, or sorry, into inches, then you take the 0.774 times 12, and you'd have, in other words, 9 feet. Oh, sorry, 9 feet, 9 inches, and then what do I have here? 0.288 fractions of an inch. All right, anyway. So what if the part that's missing is not the S? What if you have the S? So let's say, let's say theta equals mystery. R is equal to 5 centimeters, and S is equal to, I don't know, 2 centimeters. Well, once again here, we'll just take the equation, put the parts that we know in. So theta times R, so in other words, 2 centimeters is equal to mystery theta times 5 centimeters. I can just divide both sides by 5 centimeters. And I get, centimeters will cancel. I get theta equals 2/5, or in other words, 0.4 radians. Or if I wanted it in degrees, then I would do 0.4 times 180 over pi. It's equal to 22.918 degrees, if that's what I wanted. All depends on what the context is. Maybe I want degrees, maybe I want radians. So you can do it if a piece other than S is missing from the equation. As long as you have 2 parts of the equation, you can find the missing part. And the same thing is also true. Maybe you know theta, you know S, and you want R. But I'll leave that to you to determine. And now, let's try again with the area. So example, this one's going to be area. Okay, let's say theta equals, I just noticed, by the way, go back into the notes here when we were first writing down the formula for this, theta also in radians. Didn't note that. So theta here has to be in radians. Okay. All right, so let's say that theta equals, I don't know, 2 pi over 3, which people who have studied their way around the unit circle a bit may recognize as being 120 degrees. So let's say theta equals that. Let's say the radius is equal to, I don't know, 3 meters. Area equals what? Well, let's just find out. So the formula again was 1/2 theta r squared. So keep writing down the formulas until they sink in. And here it's just important that the theta be in radians. The most common mistake somebody might make here is using the radius in degrees without converting it first. So don't let that be you. And notice here that the square is on the piece that has the meters, so that means our units are going to be square meters, which is what every area should be. All right, what do we got here? So it looks like what we have is going to be pi over 3 times 9, which is equal to 3 square meters. Okay. And just a quick one where they're in degrees. All right, so let's say that in degrees, what we have is theta equals, I don't know, 20 degrees. Radius equals 1 kilometer. Area, who knows? All right, so once again, 1/2 theta r squared. Now the theta here is supposed to be in radians, this one isn't. So let's quickly figure that out. So theta equals 20 degrees times, I want it to not be degrees anymore, so the 180 has to go downstairs to cancel it. And then pi upstairs. And it looks like that's going to be, so those are going to cancel a little bit, and we're going to have pi over 9. Okay, now here we go. And here's where it's kind of important that radians are not they don't have a unit. They're not, you don't write it, you don't write any kind of particular unit there, because that would actually mess up the overall units of what the answer is supposed to be here. We're talking about areas, so areas should always have square units, like square kilometers, square meters, square inches, square whatevers. Unless it's already a unit of area like an acre or a hectare, it should always be a square of a length. And then times, what do we have here? It was 1 kilometer squared. So what do we have? It looks like it's going to be, so it's just going to be 1 square kilometer, pi over 18 kilometers squared. But of course, if somebody asks you how large is the dispersal pattern of such and such ray, and you say it's pi over 18 square kilometers, that would not be very helpful. They would rather you actually gave them a specific number. So I will go ahead and do the division. According to my calculations, it is 0.175, if I round it, square kilometers. All right. So that is that. One last application here. So here's just an interesting example of this from history. The ancient Greek astronomer Eratosthenes. So he was an astronomer who lived, he was Greek, and he lived in what we would now call Egypt. He traveled between Syene, which is a city in Egypt, and Alexandria, which is another city in Egypt. And one time he noticed that there was a ray of sunlight going down a well that like precisely in Syene, and then 500 miles to the north, I guess, I assume it's north, 500 miles to the north in Alexandria, he was able to measure the angle. And he used the difference in those two angles to calculate the circumference of the Earth. So Eratosthenes' calculation of Earth's circumference. So what he noticed was, so this was in ancient Greece. They didn't know the radius of the Earth at that time. They did know that the Earth was a sphere because otherwise otherwise lunar eclipses would not be perfectly circular. So they knew that the Earth had to be a sphere, but they didn't know like what size it was. That's pretty hard to tell, actually. So what we have are two cities. We have Syene and Alexandria, and they are 500 miles apart. So the two cities are 500 miles apart. One is due north of the other. And he noticed that the angle that the sun hits one of them was 7.2 degrees, as your book says, or he would have probably said it in minutes, so that'd be 7 degrees and 12 minutes, I guess. Difference between the two cities on the same day, like 1 year to the next. And so from that he was able to calculate the distance in the sun. So they're 500 miles apart, and the sun strikes them at a 7.2% or 7.2 degree difference. On the same day. So then the question is, what is the circumference of the Earth? All right, so let's think about that. So putting it into the framework of what we've been talking about here. So what do we know? What do we want? So R, we don't know that. Theta, do we know that? Almost. Well, actually, technically, we do. We just have to make sure that it sounds like the way it should. Let's say here's the sun. So basically, if it came head on here, then here it was at 7.2 degree difference. So what that means is that basically they are 7.2 degrees apart. Sorry, as the Earth is situated, and then but that 7.2 degrees corresponds to the 500 mile arc length between them. So what we have here is S equals 500 miles, theta equals 7.2 degrees, and then the question is, what is R? R equals what? And then circumference also equals what? Okay, well, let's calculate. So, first off, the theta is not in a convenient format. It is in degrees, not radians. So we need to calculate. So 7.2 times, so it is degrees, so we need it to cancel degrees. 180 on the bottom, pi on the top. Cancel, cancel, and we've got 7.2 over 180. Now, it just so happens usually we would reduce these by if they were integers both by just finding a common factor. But in order to do that, we'd first want to scale it up. If you do actually multiply these both by, actually it turns out 7.2 goes into 180. Fun fact. And so this actually happens to be pi over 25. but you don't need to know that to complete this calculation. It's just an interesting fact to know. Okay, so now let's see what that gives us for the radius. Okay, so S equals R times theta, or theta times R, either way. And so what that means here is mystery R, 500 miles, and pi over 25. So if I want to solve this for R, I would just divide by pi over 25 and see what we get. So the radius is equal to 500 divided by, here I would have to use parentheses unless I simplified my fraction in some particular way. Pi divided by 25. And what do we get? We get 3978.8. Or 0.9, let's say. Which, by the way, happens to be basically the exact figure that turns out the radius of the Earth actually is. It's 3979 miles. But the question didn't ask about the radius, it asked about the circumference. And what is the circumference? It is 2 pi radius. So let's calculate that. So it's equal to 2 pi times 500 miles pi over 25. All right. Well, you'll notice that we have pi's everywhere here. Let's just go ahead. Let's go ahead and do a little quick simplification here. So dividing by a fraction is the same as multiplying by its reciprocal. So that's 25 over pi. So I just wanted to make sure that we had our pi's in the proper canceling position, and sure enough we do. And what's that give us? Looks like it gives us 2 times 25 times 500, so it's 50 times 500, which is 25,000 miles. So the circumference is 25,000 miles, which is, in fact, basically exactly right. So the calculation that Eratosthenes did, and this was back in the year, hold on, I have it here somewhere. So this was back in the year So this, sorry, the thing I was looking at does not say the year, but Eratosthenes died in 195 before the Common Era. So 195 years before Jesus was born, Eratosthenes died. So sometime before that, he was able to calculate with incredible accuracy what turns out, in fact, to be the actual circumference of the Earth. How did he do it? By noticing the angle of difference that the sun strikes one place versus another, and then being able to use from that the actual calculation that would tell you something about the size of the Earth. So a lot of people think that it is a new discovery that the Earth is round, but actually it has been known for centuries, indeed millennia. And not only did Eratosthenes know that the Earth was round, he knew its size. So it's quite an achievement. It is something that actually your
your homework. We'll give you some experience doing on not on other planets, because once you know the radius of the Earth, there's no unknowing it. So you'll have a chance to play around with that same sort of calculation on other planets in the homework. But that is finally that. We have sucked the marrow out of section 5.1, covered all there is to cover, and so now we can call it a day. All right, well, I'll see you next time for the next episode of Math 112. Until then, bye.